All right. What we learned last class was the brilliant discovery of the existence of this function, this f prime function, that when plugging values into it, tell us tangent slope values to f, just like that. If we get these f primes, oh man, we could do so much analysis of instantaneous rates of change of functions, and we could do so much so quickly once we get the function. However, this magical formula that was developed, if we use it on an individual function by function basis, sometimes it's not so easy to use. A trig function, I don't know what to do with this, okay? But don't worry. We will be able to go straight from f, this f, to its f prime like that. Because these mathematicians did not use this formula for individual functions. Instead, they used that formula to develop rules. And these rules, we are going to spend the rest of the units learning and then applying so that we can go straight from an f to an f prime like that. And then we can do all the fun analysis of functions and their instantaneous rates of changes very quickly. Okay? And we will learn today, in like 10 minutes, why this function's tangent slope generator is simply 12x cubed plus 6x squared plus 2x plus 6. You will be able to do that. You will take all of the legwork out. What will end up happening is you will lose that like magical feeling of like the power of having a tangent slope generator, because it's going to be so easily produced starting today and moving forward. But don't lose it, okay? Because this thing, this f prime existence, the use of it is really special, okay? So hold on to that special feeling. You will learn today that the tangent slope generator of sine is just cosine. Oh man, it's cool. I can plug values into cosine and it tells me tangent slopes to sine. Oh, wow. This is awesome, huh? Okay, great. Now the first rule we are going to focus on is a rule for polynomials. It's called the power rule. These are all different polynomials. This is an x to the first. This is like an x squared, an x cubed, an x to the fourth. Power rule is our rule for polynomial tangent slope generators. Okay, now I can give you 5 minutes to create the tangent slope generators for these functions, but you should know how to do it. You did it on your quiz, so I'm just going to go through and do it. So let's look at x squared, its tangent slope generator. Okay, I got a negative slope, less negative, 0, positive, more positive, and negative, less negative, 0, positive, more positive. So I got something like this. Okay, cool. You guys can do that. X cubed, positive, 0, negative, 0, positive. Okay, positive, 0, negative, 0, positive. You guys could do this. Negative, 0, positive, 0, negative, 0, positive. All right, let's do that. Negative, 0, positive, 0, negative, 0, positive. We should start to notice something about the tangent slope generators for these polynomial functions. Just to kind of throw this one there, this is x to the first. that's a straight line, some positive values, but consistently positive. What do you notice? Discuss with your neighbors. We notice that the tangent slope generators are 1 degree less. Okay? The tangent slope generator for x to the fourth is an x cubed. The tangent slope generator for an x cubed is an x squared. The tangent slope generator for an x squared is an x. The tangent slope generator for x is just an x to the 0, a constant. Okay, great. Before we get into the power rule, because it's actually a little bit more complex than just subtract 1 from the degree, we need to talk about some notation that we will be using. And I will be saying, take the derivative in the future. Now, when I say take the derivative, what I'm really saying is find the tangent slope generator. Or find f prime, you know. Find the magical, incredible equation where if I plug in x's, I can get tangent slopes to f, the original function, okay? And we'll start with like a function. Let's say x to the fourth. This is the notation we will use that represents take the derivative. We will put a d divided by dx next to it. I use kind of like an undercase d from Greek. You won't always see that. Sometimes you will, sometimes you won't, depending on the textbook. But I will say, take the derivative. This is the notation for take the derivative. Okay? So, after we take the derivative today, you will quickly and easily say, oh, the tangent slope generator for x to the fourth, this is 4x cubed. Without having to use the crazy formula, the limit as h approaches 0 of f of x plus h minus f of x over h. You don't have to worry about that. That was used, and that allows us, the usage of that, to create this rule that will allow us to get to here. Okay? I could give you a y equals like x to the 8th and ask you to find the tangent slope generator or take the derivative. Now there's going to be two sets of notation we will use for the tangent slope generator of y. Okay? The first one should make sense to you. The tangent slope generator for y is y prime. The second one will be new to us, however, we need to embrace it and be comfortable with it, and it actually will make a lot of sense visually to us. Okay, let me show you. We will do the same thing with y, but instead of just saying y prime, I'm going to pretend like I'm multiplying things together. I'm going to take the d and like multiply it by y, whereas the dx can be multiplied by the 1 that goes underneath y that we don't see, but it's always there. And I get, after doing this multiplication, dy over dx. And I'm saying that we need to be comfortable saying y prime, oh, that's the same as dy over dx. And that, for x to the 8th, ends up just being 8x to the 7th. You might start to see the pattern. Now, before we go into the power rule, let's talk about this dy over dx. This should look kind of like something, okay, to you. It doesn't right now, but if I write this, delta y over delta x, triangle y over triangle x. What does that mean? Do you guys know that? Change in y over change in x. Good. But what does that mean? Slope. Okay. Now, I like to say that this delta, this change, is an overall change. And we know change in y over change in x is slope, but I'm going to say this is like an overall slope or a secant slope. My friends, this d right here, this means something mathematically. It actually means instant change or instantaneous change. Well, if overall change in y over overall change in x is a secant slope, what do you think an instantaneous change in y over an instantaneous change in x is? Tangent slope. Okay, great. Now, we, in the future, will be using just pieces of this. In the future, I'm going to say a dx is just a very, very small change in x, an infinitesimal x amount, the 0 plus or something like that. dy, I'll say, is a very, very small change in y, just a very infinite kind of slice going up, okay? So just remember that for the future. Okay, great. And then, reminder of what we can do with these beautiful derivative functions, which you think of as slope of the tangent generators, tangent slope generators, or you think of as instantaneous rate of change generators. You can plug in any value into this derivative function, tangent slope generating function, and get a tangent slope to the original function at that x location. And those annoying statements that you didn't write on your quiz, you don't have to write them here, but you need to know that this 3 means that this function is going up 3 y's per x, exactly at x equals -1. Not an average change over an interval, rather, this is how quickly it's moving right at this location. Okay? Okay, great. But up until now, I've been giving you the tangent slope generator. Now it's going to be your job to find the tangent slope generator. Okay? So let's learn our first rule that will help us find tangent slope generators for polynomial functions, an x to a power. Well, we immediately saw that we have to subtract 1 from the power. But it's a little more than that. The proof of why we need this little extra bit can be shown if you just look up like the proof of the power rule. It's using x to the n in the limit definition of a derivative and kind of using the binomial theorem and doing a lot of stuff like that. You will see why there needs to be an n in front of that. If you don't want to see, fine, just take my word for it. It'll be okay. Okay? What I tell students to do is you take the exponent, you bring it down first, and then you subtract 1 from the exponent. Okay, so taking the derivative of x squared, finding the tangent slope generator of x squared. Notice I just have x squared. It's not y equals x squared. Don't worry about that. It's just like this is the process that we're using. Take the 2 down, subtract 1. 2 minus 1 is 1, 2x. Take the 7, bring it down, subtract 1. Everybody do that. Tangent slope generator for x to the 7th is just 7x to the 7th. Roots are just fractional powers. Square root is just an x to the 1/2. So I could find the tangent slope generator for y equals root x because it's just a power. It's just a polynomial. Take it down, subtract 1. 1/2 x to the, okay, 1/2 minus 1. 1 is the same as 2/2, negative 1/2. Just going to leave it like that for now. We'll talk about what we can do with that later. Okay, you guys do that for this one. A cube root is just a 1/3 power. You will quickly and easily find the tangent slope generator for the cubed root of x function. And many of you will make the mistake that people doing this for the first time make. Did any of you put negative 1/3? Some of you did. If you did, you're not thinking about subtracting 1. Subtracting 1 is like subtracting 3/3. This becomes negative 2/3. So just be careful. Okay? Great. We are now able to quickly find tangent slope generators for functions. We can quickly find slopes of tangents to functions anyway. Some more rules. Derivatives of constants, like the derivative of 5. Or I'll just say k. Well, the easiest way to think about this, I think, is more visually rather than using the power rule. You could use the power rule, but I don't know if it makes much sense. Think about the equation y equals 5. It is a straight line, yes, but it is a horizontal line. What is the slope of y equals 5 everywhere? 0. The tangent slope generator for a constant is 0. Let's think about x. Well, this one you can use the power rule. Bring the 1 down, 1x, subtract 1 to the 0. Anything to the 0 power is 1. The tangent slope generator for x is just 1. Well, that should make sense too. What is the slope of y equals x? It's just 1. Okay. 2. Probably the question many people are thinking is like, what if I have something in front of x to a power, like 4 times x to the 7th? Well, it may seem obvious, but it is an important rule. Let's say I have like 5x to the 8th, and I'm trying to find its tangent slope generator. Constant multiple rule says you can leave the constant alone. Don't tell me that the derivative of 5 is 0. Don't put 0 down. Instead, just leave it alone. Take the derivative of x to the 8th, or find the tangent slope generator of x to the 8th, 8x to the 7th. But watch, I'll just be able to multiply these two to get 40x to the 7th. In the future, you will just take this 8, multiply by the 5, and then subtract 1. So for polynomial functions, that's important, and that's pretty obvious to do. But a lot of times in the future, we will forget this. And I'll remind you that if you take the derivative of a constant times a function, leave the constant alone, multiply by the derivative of the function. Okay? So you can easily find the derivative, and now we have y equals. So now we really actually are finding the tangent slope generators for this function. You are taking the derivative of y. You're saying that is y prime, or you're comfortable writing dy dx. Most students don't like to because it's more writing, and you guys are lazy. But you're comfortable seeing it and using it. And then you are taking the derivative of 4x to the 7th. Go ahead and do that. Simple. You see a 6 in front of the root x. You're not intimidated by it. You first say, okay, that can be written as 6x to the 1/2. And then you will take the derivative. of that. This I will just say is f prime. 1/2 brought down, subtract 1, 3x to the negative 1/2. We'll just leave it like that for now. What is the derivative of negative 3/2 x? Or what do you think the derivative of 5x is? Or 7x or 10x? Discuss with your neighbor what you think the derivative of 5x or negative 3/2 x is. Man, left hanging. Gosh. Cool. You were left hanging there. Yeah, I know.
We did like that dog.
All right, cool. So you've gotten enough then. It's just negative 3/2. Okay, the 1 gets brought down, then you subtract. So it's negative 3/2 times 1, x to the 0. X to the 0 is just 1. So the tangent subgenerator for this h prime is just 5. Okay, that's great. Now, reminder, some rules of exponents. We have a negative power. Talked about it last class. It's the same as the reciprocal with the positive power. This will be very important. If I start with 1 over x to the n, I will need to be able to write it as x to the negative n. Typically, we don't like negative powers. We don't like to have negative powers in our answer. But I am telling you, we will be using negative powers to find tangent slope generators. So be ready to write negative powers because we'll use them. Next thing, fractional powers. A lot of people are very intimidated by fractional powers, but you shouldn't be. Because you know the rule of a power to a power. Please discuss with your neighbors. Is x squared cubed x to the 5th or x to the 6th? It's x squared times x squared times x squared. 1, 2, 3, 4, 5, 6 x's being multiplied together. X to the 6th is correct. When you take a power to a power, you multiply them together. Okay. Well, I can set up two powers that can be multiplied to give me 2/3. Like a 1/3 squared. X to the 1/3 squared is the same as x to the 2/3 because I can multiply those together. I get 2/3. It's the same as x squared to the 1/3. You can write it using roots as well. This is the same as this one is the cubed root of x squared, or what you frequently see is x squared cube rooted. These are all, these are all the same. And it's important to know these rules because you, in this class, will be asked, without a calculator, to tell me what 8 to the 2/3 is. Discuss with your neighbors, what's 8 to the 2/3 and how do you get it?
Okay, so you take 8 and square it, 4 cube root that.
There's two ways you can do it. Ready? You could either take 8 and square it and then cube root it. Because 2 to the 1/3 is 2/3. But me personally, I do not know the cube root of 64. So that doesn't help me. But I do know what the cubed root of 8 is, and I can square that. I know 2 times 2 times 2 is 8, and then 2 squared is 4. So either way, you need to be comfortable with doing, because depending on the situation, one might be easier than the other. But usually it's easiest to do the root first, and then the power, the square, or the cube, or something. So From now on, if this doesn't make sense to you, it needs to, because we will have numbers to fractional powers, and we won't have our calculators. So, what is 9 to the 3/2? I think it's easiest to rewrite this as 9 to the 1/2 cubed. That's the square root of 9, which is positive 3 and only positive 3. 3 cubed is 27. Okay? We've embraced this. We will now use this. Now we can go back to our previous derivatives that have fractional and negative powers, and we need to be prepared to rewrite them so that they have positive powers and root notation rather than fractional notation. So there we go. The 3x to the negative 1/2, I need to be comfortable, first of all, knowing that 3 is not being taken to this negative power. It's just the x. The 3 stays where it is. The x gets moved. Okay? There's a lot of students out there that think that they're tied together and that I should move both the 3 and the x and make it 3x to the 1/2 in the denominator, but that's not true. 3 is not being taken to the 1/2 power. Let's go back and do some more. 1/2 x to the negative 1/2 can be written as 1 over 2 x to the 1/2, or we should be comfortable saying it's 1 over 2 root x. The 2 stays where it is. The x moves down to be in the denominator. 1 over 3 x to the negative 2/3. 1 over 3 x to the positive 2/3. Or be comfortable writing this as 1 over 3 cubed root of x squared. Yes, Ms. Quinn.
Do you rationalize the denominator?
You need to know how to, but it's not important. You'll have answers on multiple choice tests that are not rationalized. So the whole rationalizing business, like math teachers say you got rationalized, it's actually not that big.
So if it's a negative exponent, then we do include the coefficient?
What do you mean?
So like, if this 1/2 x to the negative 1/2, you put the 2.
Well, so notice where the 2 is.
Oh.
It's already in the denominator. I could write this beforehand as 1/2 times 1 over x to the 1/2, but then like these two fractions multiplied together gives me that. Cool? Okay, great. Now, I usually hate negative exponents, but we need to use them because the tangent slope generator of 1 over x squared is not 1 over 2x to the first. This is wrong. The power rule only works in a numerator. So we will purposefully rewrite this to be x to the negative second. And then we will take the derivative or find the tangent slope generator, giving me f prime of x. The tangent slope generator is, okay, let's be careful, bring the negative 2 down. Subtract 1. Don't make the mistake of saying this is negative 1. You are subtracting 1 from negative 2. Negative 2 minus 1 is negative 3. And again, the negative 2 is not being taken to the power. If there were parentheses, then yes, move both of them. But they are not. It's just -2 times x to the negative third power. Leave the -2 where it is. Move the x to the negative third down. This is awesome. This is incredible. We are easily able to find the tangent slope generating equation for 1 over x squared. 1 over x squared looking like this with an asymptote at 0 and everything. Turns out this tangent slope generator is just that equation. The power that we have. Okay. Let's start with these two. Let's rewrite them and then find their tangent slope generators. Yep. Now, you could write this second one, this G and the T, and like, why did I put G's and T's in there? For right now, don't worry about it. Just like do what you think you should do. Derivative of t squared 2t. For right now, that's all you need to worry about. And why didn't I put the t squared next to the 4 in one fraction? You know, because no, you can write this as 4/5 times 1 over t squared, right? I can kind of separate my fractions and then bring the t squared up so that it's like two separate things. I typically like to do that. I don't like to, I like to have a coefficient in front of my variable to a power. It doesn't matter though. You could write it with this t to the negative second up here and then do the same thing with like the -2 being multiplied by the 4 or the -2's being multiplied by the 4/5. You still get -8/5 t to the negative third or -8 over 5t cubed. And again, you could write it as -8 over 5 times 1 over t cubed, and then that t cubed gets multiplied over. This is -2x to the negative second. That is -2 over x squared. Okay? The other ones I'll do quickly. You can try to do them yourself and then look up and see if you get them. But we'll move on. After a certain point, the whole like root notation is actually more cumbersome than anything, and it's easier to just use fractional powers. So I will write the root notation just for you guys, though. In the future, I will personally be using fractional powers, and you guys can use fractional powers as well. You just need to be comfortable with making it look like a root notation. This guy I would rewrite as 7 over 3 x to the negative third. Its tangent slope generator would be -7 x to the negative fourth. Okay. Now the next rule, the sum and difference rule, seems very obvious, but not everything is obvious when finding tangent slope generators, which we will see next class, most definitely. And that is, if I have multiple things being added or subtracted, that you can just take the derivative or find the tangent slope generator for each of the individual pieces and add or subtract those together. Do we need the plus 0? No. I will be including the plus 0 just so you don't forget that we are taking the derivative of 1 and it is 0. So, oh, wait, hold on. It doesn't say take the derivative. It says find the instantaneous rate of change of the function at x equals 1. So I got to find the instantaneous rate of change of that function at x equals 1. Ooh, that seems daunting. Discuss with your neighbors. What are other words that we can use for instantaneous rate of change? The derivative, the slope of the tangent, all meaning the same thing. So don't be intimidated by this new question, which doesn't say take the derivative. You know that this is the same as this, which is the same as this new word. Okay, so let's take the derivative, getting the slope of the tangent after we plug in 1. The negative x to the 4th over 2, know that you can rewrite this as 1/2 x to the 4th. Do you have to? No. You could have just left the negative, bring the 4 down, negative 4x cubed over 2. Or you can just kind of do it all at once. 4 times negative 1/2, negative 2x cubed, 9x squared, 2. This is my tangent slope generator. I can generate a tangent slope by plugging in a value. At x equals 1, f of x is going up 5y's per x. Right there. Right at that specific moment. We know how quickly it's moving. Super powerful. Super applicable too. We'll start getting into physics and how calculus and physics really, really go hand in hand. You do the same thing for w, just don't stress about the variables. Say w's derivative is w prime. Say z's derivative is just the same as like x's. Let me let you in on a little tip here. I hate subtraction symbols. They are my enemy. I always make mistakes when I subtract negatives. I like to remove subtraction symbols whenever possible. I like to just change them to add the opposite, add the opposite, add the opposite. If I change that to add the opposite, that's a plus. I know I'm going to have a plus here. Now I can just worry about the sign of this, if this is a negative. So I like to multiply the negative 2 by the negative 5 right away and know, oh, I have a positive instead of subtracting a negative. You know what I mean? Maybe you don't do it that way. Whichever way you do it, just don't make mistakes. At z equals 1, it's great. 1 to the negative 3rd is just 1, so I just have 10. So you can either say w prime at 1. We'll talk about how you could say like dy dx and then x equals, but whatever. W prime of 1 is 12 minus 2 plus 10, so it's 20. All right, great. So we are now able to quickly generate tangent slope generators, quickly find instantaneous rates of change or slopes of tangents. Let's start doing stuff in a second. After being careful with these two examples, don't use the power rule in the numerator and the denominator like this. Don't use the power rule if you see a composition. Simplify first. It's not super important because we will learn different rules in the future, but if you ever see something like this, make sure you distribute everything. I simplify this and then take the tangent slope generator, find the tangent slope generator. And here I would be able to divide all of these three terms separated by addition by 4x squared. Oops, sorry. So before f prime, I'm going to rewrite f. When I divide x cubed by 4x squared, 2 of the x's cancel. I'm left with 1/4 x. When I divide 2x squared by 4x squared, I just get a half. When I divide 3x by 4x squared, 1 of the x's cancel. I'm left with 3 over 4x, or 3 over 4x to the negative first. Now I'm ready to find the tangent slope generator, and I get 1/4 plus negative 3/4 x to the negative second. Great! Now let's do some cool stuff with these tangent slope generators that we can quickly find. Like stuff we've already done, but just you're doing it. You're doing everything of it. Find the equation of the tangent line to this, there. Equation of a line. Your goal is to develop something like this. We did this on our quiz. We should be comfortable with what we need. The slope comes from the tangent slope generator. The y-coordinate comes from the function. The x-coordinate's given to you. So, let's get our point. F of 2. 2 times 2 squared, that's 4 times 2 is 8, plus 2 is 10, minus 3 is 7. Okay? F prime of x, I will find quickly. I have the power. 4x plus 1. Gosh, that's easy. I just developed the tangent slope generator, like that. Plug in 2, 9. I get y minus 7 equals 9x minus 2. Now, my friends, you will not be able to use calculators in this class. However, when you're doing homework, and I know it takes some time, it is really, really cool to see the fruits of your labor. What do I mean by that? It's really, really cool if you use your graphing calculator to graph the function and graph the tangent line you just produced. Now, do I have to solve and distribute? No. Leave the 9 and the x minus 2 and just move the minus 7 by adding 7 to both sides and see the glory that you just produced. This is really, really cool. You just did that. Really quickly, really easily, actually. Oh my goodness. Find the x locations of the line or lines tangent to x cubed minus 3x squared that are parallel to the line y equals 9x minus 2. What? It's very important to think about things visually first, especially in this class. A visual understanding of what you're trying to accomplish actually helps things tremendously, okay? I'm going to pretend like I have no idea what this looks like besides that it's a cubic, okay? I got some sort of cubic. And then I have a line, y equals 9x minus 2. This line has nothing to do with this cubic function. It's just a line. But I want to find the locations, maybe one here, maybe one here, where the slope of the tangent to this x cubed function is the exact same as the slope of this line. Right? Gosh, seems very complicated, but with the power of a tangent slope generator, it is actually very easily accomplished. Well, we know that the slope of this blue line is what? What's the slope of it? 9. Y equals mx plus b. Guess what? You could take the derivative of this, and you can see another way of getting 9 and why m is 9. So the slope of that is 9. I want to figure out when my tangent slopes equal 9. Right? Find your tangent slope generator. Okay, easily done now that we have the power rule. I'm trying to figure out when my tangent slope generator generates a slope of 9. We have an equation. Equations are our friends. We've done so much work in math solving equations. Why? Because we can actually solve and it'll help us with these situations. We don't have to guess and check. But where people fail is they like factor out 3x right away and they give me something like this. Don't do this. You only factor when you have things set equal to 0, because then you can use the 0 product property. If I have two things factored that equal 9, it does not help me whatsoever. Do not factor ever until you have something equal to 0. So 3x squared minus 6x minus 9 equals 0. Factor out of 3. Factor. I get 2 x-coordinate locations. Now I'm going to go a little bit further, because I can. I'm going to find the equations of the lines. You'll be asked to do this on your homework. So I got 2 x-coordinate locations. I'm going to have 2 equations. So I got y minus some y1. I know the slope at both of these locations is 9. I could double check. Plug in 3. Plug in -1. You'll get 9. So I got 9. I got x minus 3. And I got y minus something equals, I got 9. I got x plus 1. All I got to do is find the y coordinates. Plugging in 3, I get 27 minus 27. Okay, so this one's 0. That's nice. Plugging in -1, I get -1 minus 3. That's -4. I do this because I want to see what I'm about to show you, which is with these nice graphing calculators with the colored lines, really spectacular. We are going to see not only our cubic, x cubed minus 3x squared, but we will also see the 9x minus 2, which is just a random line, and then the 2 lines parallel to that line that are tangent to x cubed minus 3x squared. Ready, 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 ready? Yes, 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 yes! There's the 9x minus 2. That pink line's the tangent line at -1. That black line's the tangent line at 3. Beautiful. What else can we do? Do you remember how to find the vertex of a parabola? -b over 2a. Excellent. Excellent job. Nobody else remembered that, though. You have the power of finding that vertex a different way. Now, this is about you nothing. Do you know how to find the locations of humps of x cubed graphs? Is there a formula for that? Oh, there isn't. No, there isn't. There's a formula for the location. What do these locations have in common? Their tangent slopes are 0. This has got a tangent slope that's 0. This has got a tangent slope of 0. That's got a tangent slope of 0. We now have alternate approaches to doing things that we were just told, this is how you do this. Use negative b over 2a. It's like, what is that? Well, why? Actually comes from the Pythagorean theorem, but don't worry about that. Watch. When does this have a horizontal tangent? Where is the vertex? Find the tangent slope generator. See when the tangent slope generator produces a horizontal tangent, which is 0. Set up an equation. Solve. Negative b over 2a. 4. I got 4, just a different approach. But look at this. Can't do this with any equation. We got a different question. Gotta move it up because I ran out of space. Please find the x-coordinate locations, just find the x-coordinate locations of the humps to this x cubed graph. Go. You can do it. Can't use negative b over 2a, not with this. See where our tangent slope generator generates a slope of 0. These tangent slope generators are super powerful. They can help us analyze functions really quickly. Find really, really interesting locations of characteristics of functions, like the humps of this cubic. 1/3 x cubed minus 2x squared minus 5x. I don't think it fits. But look, x equals -1, one hump. Let me go down. Might be too much. No. X equals 5. Boom. Okay? All through the power of these tangent slope generators. This is a tough question. A great question, though. I am starting with a line. It's very important to visualize this. It says find k such that the line y equals 4x minus 9. Here's the line 4x minus 9. Is tangent to the function f of x equals x squared minus kx. Okay? So what I'm doing now is I'm taking a parabola and I need to adjust the parabola, whether it's getting wider or shifting it, so that the meets up with this line. Well, this is interesting. Okay, so we kind of understand that. It's like I have an equation depending on k. This can be anywhere, but I need it to fit so that it's just like that. Well, here's the key. There are two things that this parabola and this line share. Think about it for a second. There are two things that the parabola and the line share. Anybody give me one of the things that they share? They share a point. That means the y-coordinate at some x will equal this y-coordinate at some x. The y's will equal the y's for some x. You can set the two equations equal to each other. What else do they share? The slope of the tangent to f of x needs to equal the slope of that line. Exactly. Very good, Ryan. A shared slope. The y's need to equal each other, that's the point, but also the y primes need to equal each other. There's the slope. The slope of the line, you know, mx plus b. Well, take the derivative of 4x minus 9, you get 4. Take the derivative of x squared minus kx, you get 2x minus k. Ugh. What do I do now? You do the thing with the arrows. Exactly. What is that thing called? It's the S word. Substitution. We can solve for a variable. Let's solve for k, because I can only replace it in one location. I'll add k, subtract 4. K is equal to 2x minus 4. And then you will substitute it in here. Now, this is a little bit more difficult than the one you're going to have on your homework and your quiz. But it's important to be able to do it. Be careful with the distribution of this negative sign. Watch. I get x squared. I'm going to say minus. I'm going to distribute the x first. And it's 2x squared minus 4x. Then I'm going to distribute the negative sign. So 4x minus 9 equals x squared minus 2x squared plus 4x. Now, I hope you realize this. All these steps that I'm doing, which are very, very simple modifications, I am doing so that I get this problem right, not because I'm showing you. As a teacher, a lot of students think that teachers do stuff because like it's step by step, and then when you guys try it at home, you try to do a lot of steps really quickly. And then you make mistakes. Can't make mistakes in this class. I literally, if I was given this problem on a test to show how well I know calculus, I would be doing every single one of these steps to make sure I'm getting everything correct. Okay? So, math teachers say, oh, show your work, and you're like, oh, I don't have to show my work. I'm like, I'm telling you, you got to show your work for an equation like this, because if you make one little mistake, you're going to mess up. Now, this is negative x squared, and this is negative 9 after I subtract the 4 x's. Oh my gosh, look at how that works out. X squared, x equals plus or minus 3. When we solve x squared equals a number, we need a plus or minus square root, because the square root of x squared is plus or minus x. It's the absolute value of x. The square root of 9 is just 3, but it's important that the square root of x squared, the square root of x squared, this is where the plus or minus comes into play, right here. Square root of 9 is just 3, and then you move over the plus or minus. That's not our answer, though. We wanted to find k. K equals 6 minus 4, which is 2, and negative 6 minus 4, which is negative 10. And like, yeah, that's satisfying, but you know what's really satisfying? Graphing and seeing. Watch. 2 parabolas will end up having the line 4x minus 9 be tangent to it. There is x squared, 2 parabolas in this form, minus 2x, and then there's x squared plus 10x. Well, that was pretty phenomenal, actually, right there. So let's see if it works in Zoom Standard. No. Gosh, there's one, there's the other. Both of them end up being tangent to that line. Awesome. Okay. Moving on. We'll finish things pretty quickly here. Differentiability or differentiable means having a tangent slope. It's important to know that not every function at every single location will have a tangent slope, okay? You do not have a tangent slope at these locations. So this is what we'll focus on when you do not have a tangent slope. And they're just specific locations. There's no tangent slope if you have a discontinuity. So if you have a hole, you do not have a tangent slope at the location of the hole. Only here do you not have a tangent slope. If you have a jump, you do not have a tangent slope at the location of the jump. Even though you might have a function value, even though it looks like the slopes are approaching the same value, you do not have a tangent slope there at the jump because it's a discontinuity. At an asymptote, obviously, you do not have a tangent slope. There is no point. So at the x location of the asymptote. There's another situation where you don't have a tangent slope. And that's if your graph has a sharp point or a cusp. Now, let me show you something like that. At this location, you do not have a tangent slope. Why? Well, try to think about the tangent slopes leading up to that point. Positive, 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 positive. But then on the other side, negative, negative, not approaching the same value at that location. So it's kind of like one way or the other. If you look to the left, it'd be one way. If you look to the right, it'd be the other way. But at the location, it's like the limit's not approaching the same value. Okay? So we're going to go back to these piecewise functions that we had. And just like in Unit 1, we're going to analyze them, and we're going to find certain values, A and B, but not that the function is continuous everywhere. We're going to make sure the function is differentiable everywhere. That means the tangent slope exists everywhere. Now, this x cubed, it'll have tangent slopes everywhere. The x squared, it'll have tangent slopes everywhere. They don't have sharp points. The only point that we're concerning ourselves with, just like with continuity, is this point right here. But we are going to have two things to check and to make sure of. The first thing we need to make sure is that the pieces meet up with each other and your function is continuous. Remember how I use f(1) and f(2)? We're going to keep doing that. This first piece needs to have the same y coordinate as the second piece when we use 2. The second thing I need to make sure of is that I don't have a sharp point. Because I have to make sure that when the pieces do meet up, this x cubed and this x squared, they don't meet up like this and create a sharp point. This would be bad. We have to manipulate these functions so that they meet up in such a way so that it's nice and smooth. So maybe it's something like that. I don't know. But that's the key. Now, to make sure that there's no sharp point, we need to make sure the slopes at 2 will approach the same value. So the y's need to meet and the slopes need to meet up. Now, let's look at the first piece's derivative. A is just a number. Remember that. So you can just leave the a alone. Derivative of x cubed, 3x squared. Or you can write it 3ax squared. This is the tangent slope generator for f(1 prime). Don't forget, we're focusing on x equals 2. Plug in 2, I get 4 times 3, 12, 12a. The other piece, tangent slope generator for x squared, 2x. What's the tangent slope generator for B? 0. Very good. Very, very good if you got that immediately, because B is just a number. It's not x. A lot of people think the derivative is 1, but B is a number. And since B is a number, its derivative is 0. So 2x plus 0 at 2 gives us 4. We can solve for A. We can then solve for B. Okay, I'll do the other one real quick. If you want to try it by yourself, great. If you just want to follow along, great. There's a lot of different ways to do this. You don't have to do it this way. All right, finishing up just a little bit more. The tangent slope generators for sine and for cosine. Okay, now this is what's fascinating. I told you this at the beginning of class, but we'll be able to visually see it. I'm going to sketch the f prime function, just like we did with like the first kind of polynomials, but I'm going to do it for sine. And I'm just going to sketch it right on top of it. So like if I see a tangent slope of 0, I'm going to put the point 0. Tangent slope of 0, 0, tangent slope of 0, 0, tangent slope of 0, 0. And I'm telling you that at the other extremes, like 0 pi, 2 pi, negative 2 pi, these slopes are either positive 1 or negative 1. So this is positive 1. This is negative 1. I'm going to plot negative 1. This is positive 1. This slope is negative 1. This slope here is positive 1. And I'll connect these points. There's f prime in red. I'll let you catch up there. It looks just like sine. The value at x equals 0 is 1. The value at x equals pi over 2 is 0. The value at pi is negative 1. Which function has those values? Cosine. The tangent slope generator for sine is simply cosine. Gosh, that's pretty phenomenal and just crazy if you think about it. You're telling me just like cosine will tell me how quickly sine is going up and down. Really cool. Let's do it for, if the tangent slope generator for sine is cosine, probably the tangent slope generator for cosine is sine. Let's see. 0, 0. That looks like 0. That looks like 0. That looks like 0. So I got a 0, a 0, a 0. Okay, so far so good. You know, this looks like sine. If it pops up and then down and then up, I got sine. Okay, but let's see. Oh, that's a negative slope. I need to be going down first. That's a positive slope. Okay, so I need to go up there. See, that's the positive slope, so I'm up. That's the negative slope, so I'm down. I wanted it to go like this, right? That's sine, but it's not doing that. What is it? The opposite of sine. It's negative sine. That's cool and weird and interesting. The tangent slope generator for sine is cosine. However, the tangent slope generator for cosine is the opposite of sine. So I could ask you, like, what is the instantaneous rate of change of sine at pi over 4? You'd be like, well, tangent slope generator, which gives me the instantaneous rate of change of sine is cosine. Cosine of pi over 4 is just root 2 over 2. Sine has a y-coordinate, pi over 4 root 2 over 2. Yeah, right here. Pi over 4 root 2 over 2. And the slope of that line is also root 2 over 2. That's pretty cool. I could ask you the same thing for cosine. So cosine has the point root 2 over 2 at x equals pi over 4. Is its tangent slope also positive root 2 over 2? No. It is negative root 2 over 2. Cosine has the point pi over 4 root 2 over 2. But notice we are going down. There you go. Pretty cool. Just be careful when you're taking derivatives. This is where the constant multiple rule is very important. 2 sine x. Leave the 2. Multiply by the derivative of sine x. 3x plus the 3. You plug any value into that to find the tangent slope generator, or the tangent slope for 2 sine x plus 3. Be careful with sines. Remember, the derivative of cosine is negative sine. The negative 1/2 times the negative sine makes it a positive 1/2 sine x. For this guy, if you have a negative 3 sine, the derivative would be negative 3 times positive cosine. So that stays as negative 3. You have a negative cosine, its derivative positive sine. That would be the tangent slope generator for negative 3 sine x minus cos x.
How come this one is all about this again?
Because the negative 1/2 stays. So that stays. And the tangent slope generator for cosine is negative sine. So the negative times the negative makes it a positive. Cool. Okay, I could have the same type of question that I asked before, just with sine and cosine. So piecewise function, make sure it's differentiable. I'll just do this so you guys can follow along or do it yourself. We got the two things, the continuity part and the no sharp point part. That's easy. Phase 2 be a 0. Cool. 2 cosine x will meet up with x squared minus 2. No, sorry, x squared plus 2. Nicely. Here's